All right, welcome everyone to the latest installment of the Optimization Data Science Seminar. Today, we're pleased to have Philippe Rigoulet from MIT. He's a professor of mathematics there. He received his PhD in 2006 from University of Paris the Sixth. And he has worked on a number of things over the years. I've first met Philippe maybe 11 years ago at University of Wisconsin. He was giving an invited lecture there. At that point, he was working on optimization and machine learning, and now he's working a lot on optimal transport. And so it's just been a really fascinating ride watching his research. As a little anecdote, I think I got maybe a 15-minute slot or something with Philippe as a very young graduate student, and I gave him a little spiel on one of my papers, and then I think 2 or 3 years later, we were in a passing conversation, and I said, yeah, but this is just really hard and slow to do. He's like, but no, wait, you told me 2 years ago that your proof was just a linear program, and it was very efficient. And I was just amazed at that he remembered this very passing conversation. And he just really cares about students and grad students, so I was really glad that I was able to get so many students on the schedule today. But with that, I will give it away.
Thank you, Kevin. Thanks for hosting me and everyone for inviting me. It's my first time in UW, actually. I'm really excited. View is pretty impressive. So I was given a bit of a list of constraints well, not really given, but I tried to establish some constraints in terms of my talk, and it had to be at the intersection of statistics, computer science, and optimization. And I think I actually succeeded. Well, you'll tell me. And optimal transport is actually a way to do this. Well, I mean, you hear optimal. So there's some optimization, and then there's, and this is a very mathematical field, and I will actually migrate towards statistical applications of this question towards the end of my talk. It's meant to be a fairly pedestrian introduction to a lot of concepts. I will, as every good talk, mostly talk about somebody else's results. And so, I will tell you about some of the things that fascinate me in optimal transport, and towards the end, I will sort of converge to the applications of these tools that I've made to some statistical questions. Okay? So please feel free to interrupt me if there's anything that's unclear. It should probably not be the case. So let's start with an outline and see what our roadmap is for today. So we'll talk about first the Wasserstein space of probability distributions. Okay, so how we can think of the probability distributions endowed with a particular geometry as a space, so a curved space. Then, what do we want to do on this space? Well, we'll try to actually talk about do some differential calculus, compute some gradients of functions defined on the space, and that's going to give us the notion of Wasserstein gradient. And once I give you a Wasserstein gradient, if you're an optimizer, you're going to run a Wasserstein gradient descent, or here we'll talk about flows, which is the continuous time and slightly more elegant analog to it that prevent me from, or that save me from having to deal with time discretizations, which are obviously important in practice, but maybe secondary for the purpose of this talk. Okay? So I said I was going to start talking about some geometry. And usually when my students tell me, oh, I have a geometry, I ask them, okay, what's the midpoint between this and that, right? If you want to define to me a geometry, you have to tell me what's halfway between two things. From there, I can reconstruct everything. Okay, so let's start with some simple example. It's late in the day. So if I ask you the midpoint between two numbers, then you actually have calculus to do this, okay? So you don't have to actually think too hard and think geometrically about this. You just turn this problem into a arithmetic question, and don't pull out your calculators. The answer's here. And so we know how to compute the midpoint between two numbers. And from there, everybody, my 9-year-old daughter certainly knows how to do this. But maybe we've graduated from that, and we can do averages between more complex objects like vectors. Okay, and so we have Euclidean calculus on how to do this. It's a linear space, and so I can tell you what the average between two vectors is. Now, if I make the stakes a little higher and I say, okay, what is the midpoint between shapes? Then you can write this, but it doesn't make any sense, and it's not really clear what the answer to this is. Okay, so the first thing you might want to do is to think, okay, well, I mean, I can actually turn this shapes into vectors. I can vectorize my images and just output the average of the two vectors. And it's going to give you something like this, which is maybe not the only possible answer. I mean, it is one answer, but there might be some geometrically more relevant ways to answer this question, and we're going to try to explore them. And this is not just a theoretical question. You could actually think of it as being a relevant, practically relevant question. If I think of having a bunch of brain scans, I'm asking you what is the average brain scan, then maybe you want to have something that's not just superposing the two images. And in general, there's lots of types of images that are not living in some linear space for which you might want to have a geometrically relevant notion of average or midpoint. And what's nice about, or the subset of these questions I'm going to be considering are ones for which there's actually a common umbrella framework where we can actually encode these objects as probability distributions, and it will be sufficient for our purposes to think about the average of probability distributions. Okay? And so those include LiDAR, curves, meshes, etc. So moving away from applications now, I want to think about the notions of average between probability distributions. Okay, so here are two probability distributions on R2, and I can ask you what is the average, and they have densities, so you could just do what we've been taught to do, which is to just tell me 1/2 of the first density plus 1/2 of the second density. That's the notion of mixture, right? If I wanted to draw from this mixture, I would flip a coin, and with probably 1/2 draw from this guy and with 1/2 from that guy, and that would be a density that has about this shape. Okay, so that's one notion of average, which in fact is exactly commensurate with the notion of average, which was superimposing the two things, right? We've just taken this guy, that guy, we've put them on the same plot, and that's exactly what we did. But we want the circle. We don't want the superposition of the two ellipses. And the answer to this question actually lies in the Wasserstein space. Okay, so this point right here is the Wasserstein average between this mu and that mu. And as I said, if you give me one midpoint, I can actually iterate this and compute the midpoint between this guy and that guy. It's going to give me this and keep going until I actually get a full-blown curve between those things. This curve will be a geodesic, okay? And so that gives me a geodesic, and in the Wasserstein space, there's lots of nice properties about geodesics, and in particular, they have the nice property to be unique in the space we're going to be looking at. So this object here, of course, starts from the fact that I told you how to compute this one midpoint. And so let's just look a little closer on how to do it. So if I give you two probability distributions, how do I compute that midpoint up there? And I claim in particular it's not just taking the average of the densities. So what is it? Well, that's where optimal transport enters the picture. So I used to have to give slides to introduce optimal transport. You have the Kantorovich Institute here. I'm sure they've been explaining to you how to shovel sand from one part of the space to the campus to the other many times. And so I did not bring my shovel. I will just give you the formula, which tells you that optimal transport is the question of finding a transport map here. So sorry for the Kantorovich Institute. I'm from France, so it's the Monge Institute for me. And so I have an x, and I push it to t of x, which is a valid push forward, so that if x is distributed according to mu, then t of x has to be distributed according to nu. Many ways to do this, and I'm going to select the one that minimizes the expected square distance between x and its image, t of x. Okay, so once I do this, I'm going to have some optimal transport map that comes out of it under some technical conditions. And that's going to give me a way to couple an x drawn from mu to a y drawn from nu, and this y I will take it to be this optimal t applied to x. Okay? And once I have it, the geodesic between mu and nu is actually just the linear combination of the two extreme random variables. Okay? So here I'm actually telling you how to sample. I'm describing the random variable that has this law, mu t, and it's 1 minus tx plus t of x. Okay? So that's just, I find an optimal coupling, and then I take a convex combination of the two random variables. The distribution of that object, I will say that this is actually the point that's along the geodesic. So in particular, if t is equal to 1/2, the distribution of 1/2 x plus 1/2 t of x is actually the midpoint between mu and nu. Okay? So once I have this, so now I've made some, right? So I had a bunch of points which were probability distributions. Now I describe, in fact, this describes the distance between these distributions, or square distance, and now I have midpoints between these distributions. And I would like to describe the space that all these things put together actually give for me. And so this space is called the Wasserstein space. So we've seen how to describe the geodesic between 2 points. So now I want to have time 0 and time 1, so I don't have mu and nu. I'm going to have mu 0 and mu 1. Okay? So I have this geodesic mu 0 from mu 0 to mu 1. So we've just done this. And if I give you a geodesic, in fact, what you have is an initial velocity, right? A geodesic here will always be a constant speed geodesic for me. And so if I tell you the initial velocity it's telling you the entire curve. So what is the nature of an initial velocity of such a curve? Okay? So it's something that looks like, d partial mu t essentially, but really we'll identify it to the optimal transport map. And I'm going to remove the identity. So this is called a displacement map rather than a transport map. And so the initial velocity of this curve is precisely the optimal transport map between mu 0 to mu 1 minus the identity. Okay, so where does this live? Well, I mean, with some intuitive notion of Riemannian geometry, this lives in the tangent plane or tangent space of the Wasserstein space at mu 0. And so those maps, which is a map from RD to RD in our case, this will be kind of a tangent vector, right? That's an initial velocity. Okay, so that's the way you want to think about this thing. Actually, this positive curvature of the space is correct. This is a positively curved space, so you want to think about it like some sort of a sphere. Okay, so now I have my initial velocity, and I would like to talk about the velocity at any point in time for any curve. Okay, not necessarily just the geodesic. And so when I do this, that gives me a full-blown differential structure, right? If I tell you what is the velocity at any point of any curve, I've actually described all the possible tangent vectors of a point in the Wasserstein space, right? And so that gives me a full-blown differential structure on the Wasserstein space. So I remember when I first read these papers by Lott and Villani and Sturm, and they say, we're going to do a synthetic notion of Ricci curvature for metric spaces. I was getting there, and I was like, okay, a metric space is a graph. Where is it? And then I was like, oh, okay, actually, they have, it's all geodesic spaces, and they have like full-blown differential structure for this. And so this is what we have. We're much more than a metric space. So Wasserstein is a metric indeed, but it's much more than a metric space. So this differential structure is a very good step, right? And I'm almost there to have a Riemannian structure. All I have to do is to actually tell you how to measure inner product between those velocity vectors at each point. And if I do this, I'm actually essentially giving you a Riemannian structure. So if I start adding this Riemannian metric, all right, so I need a connection. I'm not going to go into this. That gives me a sort of pseudo-Riemannian structure on the space of probability distributions. Why pseudo-Riemannian? Well, because the Riemannian manifold has to have finite dimension, which is the same everywhere, and it's certainly not the case of the Wasserstein space, which is an infinite dimensional object. In some parts of the space, it's finite dimensional. I mean, it's a complicated object, but I have basically some of the ingredients of what makes a Riemannian manifold, and that's what I'm going to be needing to do all this like optimization on this space. And this was the remarkable work of Felix Soto in a series of work starting around 2000, and he's really done some really creative and interesting work. So in his honor, this line of work where we actually compute objects on this space using this differential structure is now referred to as autocalculus. Okay, and autocalculus is really a way to apply your good old chain rule and product rule and things like this on the space of probability measures. So we're going to get into a little bit into the weeds of this, and so the starting point, and don't be afraid, is going to be the continuity equation, which is a PDE. A few years ago, I did not know anything about PDEs, certainly not. I was actually afraid of PDEs. I didn't want to hear about them, and so basically, this PDE is describing you what is a curve, basically. Okay, so if I want to describe a curve in the Wasserstein space, one way to do it is to tell you how a point evolves from mu 0 to mu 1 in a dynamic way, right? All I have to tell you is what are the small time variations of mu at each point. Where do I go from this point mu t? Well, it's partial t of mu t equal to something. Well, this very much looks like what a PDE looks like, okay? And so this PDE will be this continuity equation. And what is this specific PDE? It's a very simple object. So it looks like this, okay? So it tells you that this partial t mu t is minus this divergence. So let's pause for a second. This is one of those different multivariate differential calculus objects, divergence. But before it doesn't really matter at this point what this object is. What's important is to see what are the ingredients, okay? So I'm at point mu t, and I'm telling you how mu t moves. And the other ingredient that I have is this ft. Here, ft is a vector field. So it's an object that takes a point in RD and telling you where to go into RD, essentially. And I'm telling you how a point in RD, xt, evolves according to this time-varying vector field ft. Okay, so I apply ft at xt, and it's basically, think of this as a velocity field for particles that move in RD. Okay, and so what this continuity equation is telling me if you have a family of particles, each of them is subject to ft at its point, then their joint distribution is going to evolve into something, and the evolution of this distribution is actually given by this partial differential equation. So pictorially, it looks like this. I have two perspectives on the same object. The first one is how those particles move. Okay, so think of each particle being distributed according to mu t, right? Think of it as a gas, essentially, where the particles are moving. X dot t moves according to this vector field ft of xt. Looks like this, right? Everybody has their own vector field. It's pretty complex, right? Time varying anything at any point. And so this ft induces a velocity field in my Wasserstein space. And the sense in which I mean this is that the partial t of mu t is minus, I have to push it through this minus divergence of mu t and something. And now if my particles evolve according to this velocity field, then that basically translates into an evolution of mu t along this curve that's described by this partial differential equation. Yes?
Here, do we identify the measure with its Radon-Nikodym derivative? Or
Yeah, so I will do this quite a bit, actually, in many instances. So this can be done in a weak sense. But every time it's convenient, it will identify mu t to the density of mu t with respect to Lebesgue measure on RD. That's correct. Thank you. Is there any other question? Yes?
So are you identifying like the tangent space at mu t with all these FTs and then flowing? Or
Yeah, so there's two different things. So if you ask Villani, it's probably going to tell you I don't do math anymore, but if you ask Villani 10 years ago, he would tell you that what a velocity field in Wasserstein space is this whole minus divergence stuff, right? Because it's really telling you how mu t is moving. But if you look at this guy, the only thing that actually matters is ft. And so I'm just extracting the parameter that actually changes from one velocity field to another, and I say this velocity field is ft, okay? What is ft? It's really a velocity field on the space of particles. Okay, so the nature of it is really a map from RD to RD. That's what ft is. And I say that this is the velocity field in the Wasserstein space. Okay, so the arrow that put ft in this space was sort of me cheating a bit, right? But it's how actually my Wasserstein gradient will be such an ft. That's what I want to think about it. But if you really want it to be formal, it should really be minus div mu t ft. Okay, so now that I have this differential equation, this PDE, sorry, I can actually start doing autocalculus because I want to be able to compute what the gradient of a functional, right? So I have a function that takes a probability distribution and returns a number. Okay, let's think of some objects that do this. The expectation of a random variable, right? If you give me a measure, I turn it into a number. That's the expectation. I can do the variance. I can do any moment I want. I could do the entropy. I could do, right? So just stuff that takes a random variable, sorry, a distribution and turns a number. All right, so I'm going to call this script f. It's a functional. And I want to know how this functional evolves, okay, according to time. Okay, so I have this curve mu t, and I look at partial t of f of mu t. Why do I do this? Because if I can find this like weird gradient stuff of ft mu t such that the inner product, such that this variation of ft is this gradient stuff times ft, which is my velocity field at mu t. So I haven't told you what this inner product is, but let's say at mu t, then if this works for any curves with initial velocity, with velocity ft at mu t, then by definition, this is what the gradient actually is this thing that's in the cotangent space, right? So I have ft in the tangent space, and whatever this thing is, the dual object is, has to be my gradient. So if I can find something there, I will say, well, ta-da, this has to be my gradient. Okay, so let's do it. Okay, so let's just compute this partial t of f of mu t. Okay, so I just apply the chain rule. Partial t of mu t is just the first variation, so that's basically the derivative of in L2, right? So you think of just f as a you pretend that this guy is at x, essentially, and you just take the derivative with respect to x. That gives you the first variation. And then by chain rule, you actually pick up the partial derivative with respect to mu t. Okay, and then I take the expectation of this guy. Okay, so now I have partial t of mu t, which is driven by my continuity equation. So I just substitute partial t of mu t with minus div mu t ft. Okay, so that's what I get from the continuity equation. And then what I do is that I apply the only tool I ever needed or will probably ever need in PD, which is integration by parts. Okay, and so, I mean, as long as you don't care about whether they're well posed, that's really all you need. Oops. Oh, that's right, I'm recorded. So I just take my divergence, I push it here, so the minus sign goes away from integration by parts, and I end up with the gradient of the first variation against whatever was left here, right? So mu t ft, and I just permute them. So I take ft and I take mu t out of this inner product. Okay? So that's just integration by parts. And so now what I've worked, so I put back what I had. So I've shown that this derivative of f with respect to time is actually just this integral. And I want it to be the gradient against ft. So what is the natural identification I have to do? Well, I have to say that the gradient, the Wasserstein gradient, is this gradient of first variation of f. And I also have somehow, for this to be able to do, I have to say that the local inner product that I have on the tangent space at mu t is just L2 with respect to mu t. Okay? And so that's what I do. I put the L2 metric on the tangent space at mu t. And that allows me to say that the Wasserstein gradient, by pure identification, is just the gradient of the first variation of my functional at mu t. Okay? So that's it. That's the calculus rule. I've shown you how to do this. If you were a freshman, you would just learn how to do this, right? You just learn the rules of calculus without understanding them. But I've actually shown you the, f of x plus h minus f of x divided by h, really. That's what I just showed you. Okay, and so what is a Wasserstein gradient now in terms of what object, mathematical object it is? Well, it's a gradient. So the first variation is still a functional. And so the gradient of a functional now becomes just a gradient vector field. Okay, so it's just something that maps RD to RD. So that's something, this is really a function of something, right? This f of mu, so delta f is not a functional. Delta f is a function on RD, and now I take the gradient of this function. So this is really gradient of delta of f of mu at point x. Okay, so a Wasserstein gradient for me is a gradient vector field. Okay, and that's what we set out to do in the first place. Again, if you are Villani, you would say it's minus divergence of mu t times this vector field. Okay, so let's apply calculus. Now we can just have a library of functions, functionals on the space of probability measures, and let's apply those rules. Okay, here's a simple functional. I just integrate a function d mu. For example, all the moments that I gave you as examples, v was x, x squared, etc. And so let's see what the Wasserstein gradient of this guy is. Well, I first compute the first variation. You'll easily check that it's v itself. And so what is the Wasserstein gradient? Well, it's grad v. Okay. You could look at interaction energies that just take the expectation of k of x minus y, where x and y are independent, drawn according to mu. First variation is just this convolution of k with mu, and therefore the Wasserstein gradient is the gradient of this convolution. Okay? Another example that goes back to this brain scan examples, which is the barycenter functional. All right, so what is the barycenter functional? So here I said that the midpoint is just the measure mu that minimizes the sum of square distances divided by 2, right? So that's the center of gravity. It's called the barycenter, and rather than having only nu1 and nu2, I could really do it with probably 1/2 each. I could just take a bunch of nus and put a weight p of nu on each of them, take the expectation and minimize the expected square distance to some reference point. So I'm looking to the point that's minimizing the expected square distance. That's the center of gravity of mu with respect to this Wasserstein distance. And that's really what drives these fancy pictures that have been done by my colleague Justin Solomon. So this guy here, this duck with a hole in its head, is the average of a donut and a duck. Okay, and you can just change the weights, and here the weights are just captured by p. Okay, so here, same thing. You have a functional. It's the integral of the squared Wasserstein distance from dot to nu. I can compute its Wasserstein gradient, and if you carry out the analysis, you will see that it's the integral of this negative displacement map from mu to nu integrated against dp. Okay, I can keep going, but rather than doing them one at a time, let me give you a table for the ones that will actually be relevant for the rest of this talk. Okay, so the ones that will be relevant, so the examples I will talk about are sampling. I don't know if Roach is here. She's a specialist of sampling, right? By sampling, I mean sampling from, say, a posterior distribution. And it's the KL divergence to some target measure nu. Okay, that's my functional. So it's a functional of mu to nu. And here you will see, we'll see that, well, we will see. I'm telling you that if you compute, and this should take you really a minute, the Wasserstein gradient is the gradient of the log of the density of mu with respect to nu. So that's for sampling. For maximum likelihood, actually, the target measure is the one you get your data from. And that's usually the first argument in the KL. This fact, some people call this the reverse KL. In fact, so that's the KL from nu to mu. And in that case, you can actually, again, compute the Wasserstein gradient. And then you get minus the gradient. There's no log anymore of the density between nu and mu. And another example we'll see towards the end is so-called non-parametric maximum likelihood, which is a maximum likelihood problem over Gaussian mixtures. All right, so here you see what you have. You have the negative log likelihood, right? That's the average log likelihood, 1 over n sum of the logs. And those are the densities at each observation zi. What are the densities? It's mu composed with a Gaussian. Okay? So what I'm trying to do here is to find the measure mu, which when composed with a Gaussian is the most likely to have generated my data. All right? It's called non-parametric maximum likelihood. And it's basically for non-parametric mixture models where you think that your data is a potentially continuous distribution convolved with a Gaussian, rather than just a discrete distribution like we're used to seeing in Gaussian mixture models. All right, and here you can also compute what the Wasserstein gradient looks like. Okay, why do we compute Wasserstein gradients, right? It's not Calc 1, and it's because we want to be able to use them in some gradient descent schemes or gradient flow schemes. So that's what we're going to talk about now. What are Wasserstein gradient flows? Okay, so let's recap. We have some functionals, KL mu nu, KL nu mu, some log likelihood, all this stuff we've been defining with the Berry Center. From there, we were able to compute the Wasserstein gradient. And now I want to describe a Wasserstein gradient flow. So what is a Wasserstein gradient flow? Well, it's something that flows according to the negative Wasserstein gradient. But the Wasserstein gradient is a what? Well, it's a vector field on RD, right? So what flows along a vector field on RD? Well, particles on RD. And so the natural way to describe this is an ODE that tells me that each particle xt flows according to negative gradient of f at nu t applied to xt, and that's giving me my velocity of the particle. But really, that's a way to implement, that's not a Wasserstein gradient flow. A Wasserstein gradient flow really is something that tells you how a curve of measure evolves, right? It's like really an evolution of measures. And so what we really have to do is to plug this in here. And so that's, remember, the continuity equations was allowing us to do precisely this. I gave you some deterministic evolution for particles with some ft of xt, and now I just plug it in here, and that gives me, and the continuity equation, sorry, there's a minus, the minus canceled with that minus, and so it's the partial of mu t, which is the divergence of mu t against this Wasserstein gradient. Okay, so this Wasserstein gradient in general may depend on the distribution of all the particles at a given time t, and that's what's going to make things a bit challenging, right? So it's a vector field that depends on the distribution. So this PDE is sometimes called PDE of a Vlasov type, right? So PDEs that depend on the measure at a given time. Okay, so probably the most prominent example of a Wasserstein gradient flow is this Jordan, Kindler, and Otto scheme. Okay, so I'm not going to describe, I'm not going to follow chronology here. We'll just follow, what we know. Okay, so what we know is that if I give you a functional, you know how to compute the Wasserstein gradient, and so let's do it. So if I look at this functional, KL from mu to some target nu, and I'm going to assume that nu is e to the minus v. Okay, so just like some potential v. So I told you that the Wasserstein gradient was the gradient of the log of the density. And in this case, it decomposes into the gradient of v plus the gradient of log mu. Okay? So that's the Wasserstein gradient of this KL. It was in one of the tables. Okay, but not for this specific nu. Okay, so now if I do this, let's just plug it in our ODE. So if I plug it in my ODE, this is the vector field I'm getting, right? So I apply, so this guy is just a vanilla vector field. It's not even time varying, but there's also that part which is time varying and in fact depending on the distribution. And if I plug that velocity field in the continuity equation, I get the following PDE. Okay, so here I just plugged in the whole thing, right? So that was my velocity field, so I get grad v, and then I get grad log mu, so it's grad mu over mu, right? But look, there's something nice that's happening. Mu and mu cancel here, and so I have the divergence of the gradient. The divergence is sometimes called grad dot, and so I'm basically really taking the Laplacian, so the divergence of the gradient is really the Laplacian, so the trace of the Hessian of mu. Okay, and so if I simplify it, I'm getting divergence of grad mu, which is the Laplacian of mu. And in this particular PDE is actually called the Fokker-Planck equation, and it actually describes the evolution of the law of some random variable that evolves according to a Langevin diffusion. Okay, so if I only care about the marginal distribution of xt along this diffusion, which has like temporal correlations, etc., but let's say I forget, I just say, what is the distribution at time t of this Langevin diffusion? I actually get mu t, which evolves precisely according to this Fokker-Planck equation. Now this is actually, okay, this is classical Markov process theory, but in fact, if you actually look at this, I just described to you another way to actually follow this curve, which is following this like completely deterministic dynamics. All I required was to have a density. So the only randomness coming from this guy is the initial distribution of my particles, mu0. And that's a deterministic evolution, except that now the role of this is just the Laplacian part, and the role of the diffusion, which comes from this bt, is actually played by grad log of mu t. And that's really the gradient of the entropy part. So I'm actually trying to increase the entropy as I'm moving using the heat flow, essentially. And so that was the result of Jordan, Killer, and Otto to realize that, in fact, this Fokker-Planck equation is the Wasserstein gradient flow of the KL divergence to the target measure. Now, if you know your Markov process theory, you know that the Langevin diffusion is already the gradient flow of something. It's the gradient flow of the Dirichlet form, but with respect to vanilla L2. That's great. That allows you to use Poincaré to characterize rates of convergence, etc. But in fact, this enables you, what I think is really strong, is this particle interpretation that enables you to have this deterministic scheme. So there's a little star here, and the star here comes from the fact that, in fact, Jordan, Canalera, and Otto not only had this vision to do this, to show that it was not the gradient flow of something, it was the gradient flow of something more meaningful, which is this KL divergence, but it was also, what they actually did was do it without even a notion of a gradient. Actually, we had to wait until Ambrosio, Gili, and Savare started really collecting things and make it totally formal what the notion of a Wasserstein gradient actually was. What JKO did, Jordan, Killer, and Otto, was to actually use an analogy with the Euclidean case by using this proximal point method that says, well, let's just take some tiny h so that the weight on this guy is huge, and now I'm going to take the measure that minimizes my objective without moving too far from my previous guy, all right? So mu t plus h is really just mu t, a small variation of mu t that's trying to minimize, essentially. So if you think about the Lagrangian, the constrained version of this, you're just putting yourself in a small ball around mu t, and you're moving, minimizing f of mu in some small ball around mu t. And this thing, if you actually see as h goes to 0, if this guy was the squared Euclidean distance, that would be a gradient flow. And so they said, okay, let's just say that's what a Wasserstein gradient flow is. In fact, you can define it for any squared distance here. And then they showed that this scheme, mu h, converged to a curve, and this curve is actually described by Fokker-Planck. Okay, so as remarkably ingenious, you don't have a gradient, that's okay, I don't need that for a gradient flow. And this proof technique is still very much valuable because PD and existence of solutions, et cetera, is great to actually, working with PDEs is great. You can use integration by parts. You can move forward very quickly and advance your calculations. But when you actually need things to be true and exist, this is still an extremely robust theory to show that this curve exists and is the limit of something. Okay, so that's for the result of JKO, which probably is the reason why I'm still working on optimal transport. I think it's a beautiful result. And but now I'm going to try to move on to things I know how to do, which is how do we implement these things? And remember, so I claimed that, forget about Langevin. Let's say we want to implement this deterministic thing. It seems pretty nice, right? The trajectories are certainly going to be smoother than the ones that involve Brownian motion. But the problem is that this thing here is unknown. I don't know what mu t is. If I evolve one particle with Langevin, it has a distribution. I don't need to know what it is to actually find the next step, right? The Brown motion takes care of it for me. Here, I need to know the distribution at time t for each t. And so if I have one particle, I cannot do it. So how do we implement this? Well, the idea that was put forward in something called Stein variational gradient descent by Liu and Wang using other arguments, but then subsequently Liu realized that that's what they were implementing, was to evolve n particles, which somehow should give you an idea of what this joint distribution is, and they use some sort of non-parametric estimation of mu t, right? So here, following your question, mu t is the density of those particles. You could use, say, a kernel density estimation. They use some RKHS theory, but it's very close. And you can implement this, and you get this kind of things. So here, I mean, this is something, a variation on SVG that we propose, which is more stable. But really, the idea is you start with a bunch of particles, and as they go, they're going to form some sort of discretization of the target measure that you have. Okay? So, okay, so that's you know, I don't want to spend too much time on this, and the reason is because this is great, but this 2D picture is really symptomatic of what's happening with SVGD. It's a non-parametric method, and therefore it does not scale up to high dimensions very well. It's very difficult. And so there's many ways you can actually try to go around this, but the natural way when non-parametric methods don't work is to go parametric. Okay, and so
Can you say in the previous slide that they, do you have some sort of like as n goes to infinity almost sure?
yeah, so actually for SVGD, it's not known. The rates of conversion, so there should be some theory that says, you know, depending on the smoothness of your, of mu t, for example, or maybe if the target should actually determine the entire thing, you should have some theory like this. This is completely unknown. There is some theory about, like, you know, mean field convergence of Vlasov equation for interacting particle, but it's mostly for some linear, where mu enters in a linear way. But yeah, no, for this theory, there's actually absolutely, I mean, it's like, yeah, by all means, it's pretty open. Okay, so here, so I'm going to argue rather than going in that route, I'm going to try to go in a different route, which is to say, well, rather than going to think of this guy as being any smooth thing, I would estimate using a kernel density estimator, say, I'm going to actually pretend it's a Gaussian. Okay, and that's actually something that people have done without really thinking about it this way, and it's actually called variational inference. Right? What variational inference is saying, okay, you give me a posterior distribution, say, and rather than doing MCMC, which would sample stuff according to, say, something based on the Langevin diffusion and then take the average, rather what I'm going to do is to say, well, I don't really need to know pi perfectly. I really want to extract its mean and its covariance, really, because that's all I care about to do my Bayesian inference. And so I'm going to estimate it by something simple, for example, a Gaussian, for which it's very easy for me to extract mean and covariance. Okay, so, and people use other stuff like product measures, it's called mean field VI. And so here we're going to follow this idea and to say, well, okay, you have your KL divergence, KL from mu to pi, and rather than minimizing the whole thing, which will be 0 and actually give me pi, I'm going to just try to find the Gaussian that's the closest to pi. Okay, so what is it? This is really just adding a constraint to the problem that we had before. We're trying to minimize the KL from mu to pi. Now we're just trying to minimize the KL from p to pi, where p is constrained to be a Gaussian. Now there's a rule. We don't know the normalizing constant of pi, so we cannot solve this problem using the normalizing constant of pi. Okay, so for example, I could use gradient of v, so gradient of log pi or Hessian of log pi, etc., but nothing more. Okay, no normalizing constant. And so what we propose is something we call Buras JKO. So Buras is the Buras-Wasserstein space is the subspace of the Wasserstein space that consists only of Gaussian measures. And it turns out that if you can actually implement a Wasserstein gradient flow constrained to lie on the space of Gaussians, right? I mean, you're trying to solve a constraint optimization problem. You're going to just like do this constraint. And what's nice is that rather than actually having to track a whole distribution, maybe using some particles, really I have two parameters to track, the mean and the covariance of this Gaussian. And so what I can do from the Fokker-Planck equation, I can actually extract the evolution of the mean and the evolution of the covariance. And I'm doing a trick, which, so that would be Fokker-Planck if I replace this guy by the true x and the true x here instead of the y. Now I'm just going to take the y that has mean mt and covariance sigma t, the current mean and the current covariance, but I'm going to pretend they're Gaussian now. And it turns out that this thing, which is actually proposed by Sarka in the context of filtering, turns out to be, it's called unscented Camden filter, turns out to actually be Wasserstein gradient flow constrained to stay on the space of Gaussians. And what's beautiful about this is that it allows us to actually use the full-blown machinery of Wasserstein gradient flows and prove some convergence results rather than just leaving this as an heuristic and hope that this actually works. So in practice, Well, I mean, those are just coupled ODEs, right? So, I mean, I'm not even going to bother discretizing it because some people are much better than me at doing this, right? So I can use Graham-Goldzka. There's an expectation with respect to Gaussian to compute. Here we decided to use curvature rules, but you could use Monte Carlo if that would do essentially the same thing. And then now that you have this thing, you look at when you implement it, for example, in some logistic regression, it seems to actually find a Gaussian that looks pretty much like what your posterior, like the Gaussian that's the closest to your posterior. So in terms of convergence results, well, we would expect that this thing, which is a constrained Wasserstein gradient flow, constrained to Gaussian, should converge to the argmin over Gaussians of this objective function that we had. Yes, Lidit?
But this is like, so the only way I know how to do this is like a Laplace approximation. This is
That's right.
do something that's not a Laplace. Like
That is not a Laplace approximation, and in fact, you can show that it works orders of magnitude better than Laplace approximation. So Laplace approximation, so what is Laplace approximation? That's a way to approximate a distribution which is very peaked, right? So it's something of the form, it's something of the form e to the minus n times v, where n is large. So it's something that's going to peak around its global maximum. So what is the candidate Gaussian to approximate this? Well, you just say that the center of the Gaussian is the argmax, right? The mode of your distribution. And what is the covariance matrix? Well, you just take the inverse Hessian around this argmax, okay? That's the Laplace method. Well, when it comes, the problem with the Laplace method is it's very local, right? Especially when it takes the mode as opposed to the posterior mean. And so in terms of n, if you look at the distance between the mode and the mean, so you get something which is of order 1 over n. All right, so that's an object that, so this distribution has standard deviation 1 over root n. So it's actually not bad, right? I mean, 1 over root n, if you draw a random sample, you would get 1 over root n. Using the mode, you get 1 over n. But if you actually use variational inference, you get 1 over n squared. And the reason is because Laplace approximation is actually trying to find the best truncation of Taylor expansion, whereas VI is trying to find the best truncation of Hermite expansion. So that's a result we have this year with Anja Kacevich. But actually, I would love to say that this basically definitely settles VI being better than Laplace. But she actually has a forthcoming paper where she, using those Hermite expansions, she found a correction to Laplace that actually performs as well as VI in terms of orders of magnitude. So she kept on pushing these asymptotic expansions, and she actually can correct the mode. So it's not quite the mode, but there's a simple correction you can apply to the mode and get much closer to the posterior mean. Yes?
Sorry. What is the second word you're saying? The what expansion?
What is the what?
The other expansion you were
The
saying?
Hermite expansion.
Oh, Hermite expansion.
Yeah, Hermite expansion. Okay. So what are the convergence guarantees? So we expect this will converge. Well, so there's some folklore knowledge that if V is alpha strongly convex, okay, so it has like Hessian lower bounded by alpha, then this KL divergence is alpha strongly convex along the Wasserstein geodesics, okay? So the convexity of your target measure drives the convexity of your KL divergence to the target measure. Okay, so that's well known. And it turns out that the geodesics between two Gaussians stay Gaussian. So in particular, this means that so if this is true on the Wasserstein space, it's going to be true on the subspace, which is the Bures-Wasserstein space, because, I mean, it's actually a complete tautology, right? I'm just saying that the geodesics stay on the Bures-Wasserstein space. And so just by using this like pretty heavier machinery, we could just say, okay, well, if V is like this, then I have this strong convergence. I'm doing gradient flow. Okay, so when I have a gradient flow, I can actually assess its rate of convergence, and I get exponential contraction, which is like 2 times alpha, which is my strong convexity parameter. If it's strictly positive, I can get it both in the distance of PT to my target or in the gap, in my objective gap. And even if I'm actually just convex and not strongly convex, I mean, those are completely, I mean, I'm sure Dima is yawning in his head. And so if alpha is actually not strongly convex, so if I'm just convex, I change my Lyapunov function, I still get convergence of the objective, but now at a rate 1 over t. So what Dima is thinking, he says, oh, you only need strong convexity because you're not discretizing time. So if I wanted to discretize time, I would actually have to apply strong smoothness. It turns out strong smoothness, or I mean like upper bound on the Hessian of the KL, I mean, I didn't really define second order calculus, but if I were to try to think about these questions of like, is the gradient of the KL Lipschitz this is actually a much more complex question. And so discretized results are, I mean, you can do it, but it's a completely different machinery. Okay, so this is great. And, but the problem is that if you start moving away from log concave distribution and you have two modes, what's going to happen is this. Okay, it's going to just forget about one and do a very good job at the first one, but forget about the second one. So that's because Gaussians are just not good approximators of bimodal distributions. And, but what are good approximators of bimodal distributions is mixtures of Gaussians. And so we'd like to actually use mixtures of Gaussians instead. So we would like to do a Wasserstein gradient flow constrained to staying on the space of mixtures of Gaussians. So that's becoming a bit more complicated. And so we have to think about mixtures of Gaussian in a particular way. And the way we do it is as follows. So this is a mixture of Gaussian. What is a mixture of Gaussian? It's just a weighted convex combination of Gaussian densities where the weights are given by the so-called mixing measure mu. Okay, so it's just a measure on the parameters of the Gaussian. And here, this is this non-parametric mixture, right? You think it's just an infinite mixture, a continuum of mixtures. And so, and each guy here, this is a density of Gaussian. Okay, everybody's clear that this is a mixture of Gaussians, right? For example, P mu sigma could be weight 1/2 on -1 identity and and 1/2 on +1 identity, and that would give me a mixture of two Gaussians. Okay, so now what I'm going to do is I'm going to think now of this as being a measure not on any space of parameters, but on the Bures-Wasserstein space of Gaussians. Okay, so just the space that we thought about before. So what I've just done is think of this measure as being a Wasserstein over the Bures-Wasserstein. Okay, so it's a Wasserstein space over the Wasserstein space of Gaussians. Okay. And we're not the first one to do this. So there's these two papers that try to define, they called it a Wasserstein-like distance on mixtures of Gaussians. And that's a way to sort of, the problem with Wasserstein on mixture of Gaussians is it doesn't care that they're mixtures of Gaussians, and you would like something that first addresses the mean of the components and then maybe the covariance. And so they went very quickly to like finite mixtures of Gaussians, which is a bit messy. But if you stay in the continuum, it's actually a very clean object to play with. And so now what we have is a gradient flow, not of mu, of the KL of mu to pi, but of the KL of p sub mu to pi. Okay? And now this mu here lives over the Bures-Wasserstein space. Okay? So this is still a constrained problem over the Bures-Wasserstein space, except that it's not KL of mu to pi, but KL of p sub mu to pi. Okay? Now all convexity is out the window. Okay? There's not going to be any theory. There's no unique minimizers. Like, just because you can represent mixtures of Gaussians in many different ways, it's a complete mess. But you can still you can still apply the continuity equation and do your integration by parts. You can apply the autocalculus and start computing stuff. And so what I'm going to do is implement this as a system of interacting particles. But now each particle is itself a Gaussian. Okay? So this is how it goes. I here is the index of the particle at time t, and each particle now is a Gaussian with mean mt and covariance sigma t, indexed by I. And now I'm looking, and mu t will be just the empirical distribution of those parameters. Okay? So those are particles that live on the Bures-Wasserstein space, which I identify with the mean and covariance. Okay? Yeah?
I mean, some representations of a mixture of Gaussian seems clearly better than others. So this seems like, if I have a mixture of two Gaussians, it's probably better than if I represent the same distribution as a mixture of like infinite many Gaussians.
Yeah.
And so, there's no, as far as I can see, there's no selection mechanism here.
No, we don't actually select. Actually, I'll tell you some, well, not here, there's no real failure mode, but yeah, so you could actually penalize for certain parts of the space of Gaussians when you're doing this, mixture. When we implemented this actually worked pretty well. There is something that we need. I will tell you some failure modes, but I agree that there's tons of things you could do by penalizing some bad mixtures of Gaussians, absolutely, and maybe elicit some convexity for some parts of the space. But mixtures of Gaussians is notoriously non-convex, even in like extremely simple settings. Though it's mostly people have mostly studied in the context of maximum likelihood, in which case it's not the KL but the reverse KL, right? Not the same one we're looking at, but it's the same problems. Okay, so And what we show is the following. So you can actually write this. So you have a system of interacting particles where each particle is a mean and a covariance. And the way they interact is through this P mu, which is the mixture, the density of the mixture. And so you can run this. So of course, I mean, I'm not going to ask you to read those equations. It's just a system of interacting particles. And when you run this, this is what you get. Okay, so you run your, you start with a bunch of Gaussians that are all centered at random points, and he'll have a like small identity covariance matrix. And then you just like evolve this thing, and you're going to recover some distribution like this. Okay, so they just move around, and you can see, you know, this is over-parameterized, obviously. I don't run with like 4 Gaussians, but I recover what I want from a mixture, over-parameterized mixture. And, but I don't want to show you only the good thing. There's also some bad things that are happening. In particular, so here you see there's more weight on this mode than on that mode. And if I initialize too much close to that mode, then I actually get something which is not what I want. I did not get any weight on this bottom left mode when I really should get like, you know, the third amount of weight here. And so the problem is that what Wasserstein does is just really trying to push the particles to reconstruct the mass where it is. So really what it has to do is to take all these particles, move them here so they actually create the mass that I'm looking for, right? But the problem is that they hit some, you know, big energy barriers, and they cannot go there, and that's the non-convexity at play here. It's like not like some benign non-convexity. It's really getting there and stuck and getting stuck. So how can we actually overcome this? Well, here the problem is that the weight has to move from left to right, but if we could actually teleport the weight, change the weight of those particles, if they get stuck, we could say, okay, you're stuck, but let's just try to increase that weight and push the weight on another particle. That's where it should be. Then maybe we can do better. It turns out there's another geometry, which I won't go into details, which is called Wasserstein-Fischer-Rao, which allows you to evolve not only the mean and covariance, but also the weight. And it's the same evolution, but there's another, just like almost an exogenous, completely independent evolution for those weights. I mean, of course, it depends on the density itself. And this is the Fischer-Rao part. I don't like this geometry so much. It's really like taking 2 geometries and putting them together. So this is Fischer-Rao geometry, is the one that shows up in like Amari's information geometry for, you know, statistical models. So it's the Hessian of the, it's the Hessian geometry with respect to the parameters associated to the Hessian of the entropy. It's also actually the distance that's induced by this geometry is actually the Hellinger geometry. Okay, so the Hellinger distance. So if you're a statistician, you've seen that before. Okay, and so this is what you get. So without weights, as we've shown, you cannot really pick up the right thing. So this is the picture I just showed you, but with weights, I mean, here there's a small number of particles, but you actually recover the right size of your weights. Okay, so I had one more example, which was on non-parametric maximum likelihood estimator, where we reversed the KL. I'm not going to go too much into those details. This is just a maximum likelihood problem for a mixture of Gaussians. So I'd like to skip this, but basically same story. You can write a Wasserstein gradient flow that's optimizing the negative log likelihood in this case. We use the Wasserstein-Fischer-Rao geometry. Here we can even do a gradient descent without doing gradient flow. So you just alternate between a Fischer-Rao step and a Wasserstein step. And we can show some conditional convergence. So essentially show that if it converges to what we want it to converge. And I mean, there's some you know, interacting particle systems, and it works well, obviously. So to conclude, I just want to leave you with this slide. So we're actually, I taught statistical optimal transport, so this is much beyond what I'm talking, but this will be one part of this book, which will appear as some lecture notes. I enrolled my former students, Sinho Chui and Jonathan Weed, who were experts on aspects of statistical optimal transport, and embarked with me on this journey. And there will be things about, you know, convergence of the empirical to the true. There will be things about estimation of transport maps, and there will also be things about the more dynamical optimal transport related to sampling and JKO, et cetera. So the things I've told you about today. On this, thank you for your attention.
Time for questions.
So you talked about how we can also do stochastic, right? We can also simulate the Langevin equation to sample. So how do you compare all these deterministic methods to
I mean, in terms of, so, you know, I mostly do theory. Okay, actually, theory and practice. So first of all, the overwhelming part of theory is and practice is Langevin based, right? So it's like, you know, sampling, MCMC based sampling, and they're pretty much dominating, right? So in terms of practical performance, it's definitely working much better than SVGD in high dimensions. You know, we know the scaling is, say, sublinear in the dimension, really, in fact. So it's like square root D or something like this for strongly smooth and non-concave, if you can do Mala. And so that's definitely the big rain compared to SVGD. In terms of theory, as I answered to James, there's basically no theory for SVGD. I really think the reason, again, I'm recording, I shouldn't say that. The reason why SVGD exists is because it's just a cute result that like is a riff-off of a JKO, but on its own, I don't think it has any practical viability. But I do think that variational inference is actually working pretty well. And of course, you know, it depends on what the purpose of what you're actually doing is. And if you, so, you know, the mixture of Gaussian one, I wouldn't advocate for it so much because it has not too much interpretability. But really, the Gaussian one is something that will spit out a number much faster for the mean, for example, for the centering parameter. It's going to spit out a number much faster than anything you have. Maybe a bit slower than the Laplace method, but it's going to be very accurate. And you can also play with other distributions. So the big thing that people like to do is mean field, where you're actually optimizing over product distributions on each of the coordinates. The problem it has a tendency to underestimate the variance. And the reason is because if you think of your posterior as having contours or ellipsoids, what this thing is doing is like putting boxes in there. And so the size of the boxes has to be a bit too small, basically. And so people are trying to speed up variational inference to not have to carry full covariance matrix, but only not diagonal either, which is what mean field is doing, but something in between to actually take advantage of like the speed up that you might get for like some trade-off in terms of speed and accuracy that you could get. But yeah, in terms of sampling, it's very hard for me to make a convincing statement that MCMC is still not like really leading this thing, especially with you know, what Yintat and Rochi actually developed, which is like, you know, this restricted Gaussian oracle, which is really working well. And I think in practice, people really like HMC as well. So yeah, there's mostly conceptual things. For me, it was an entryway to think about other optimization problems, such as, you know, NPMLE. But yeah, JKO is really a natural entry into sampling. But yeah, I would say that other things, like optimizing other functionals, is really where the future lies, I'd say.
Have you used this at all in the context of like estimating marginal likelihoods? Because you know, you like state of the art right now, it includes stuff like, you know, doing a Laplace approximation on a non-Gaussian marginal likelihood and optimizing that, right? So
yeah.
Could you replace that with?
I haven't tried it. That's definitely sounds like a very reasonable direction to go into, but that's not something we've explored at all. Thanks.
So you showed one example where convexity like was automatic over the Wasserstein space. And I'm just wondering, like, is convexity is it common or not, like for other functionals, other examples over the Wasserstein space? Is it reasonable, or should we just forget convexity?
Yeah. Okay. So that's a very good question, right? It's not like you're developing your own ML loss and you make it convex and that's the way it works and then you just want it this way. And so I'm not a huge believer of, you know, let's elicit convexity using Wasserstein, right? Actually, if anything, I found, for example, on the PSD matrices, right? So we have Bures Wasserstein, but I found that the log-det geometry, so the Hessian of the log-det geometry actually tends to do better at this job, though they're not actually comparable, I checked. But so I wouldn't say, you know, you can find convexity where it's not using this Wasserstein geometry. What I would say, though, is you could use convexity the same way you've been using convexity in the Euclidean space by designing your own losses. Now, here I've mostly talked about things where the loss has been designed for you, but you can really think of, like, I think this is really the birth of like thinking about functionals over probability spaces. And I think we're going to be able to design them more than not. Okay, so for example, we've been thinking about transformers as optimizing some functional over the space of probability measures in terms of the interacting dynamical system, and we look at some setup dynamics, but then you could actually really change the dynamics so that you actually get the convexity that you want. Well, I guess in that case we want the opposite of convexity, but this is something you could actually really foresee to design, and I really think this is where it is, rather than like that, where there's going to be the most discoveries is in new problems where we design our own functionals rather than like trying to look at like classical functionals like KL or something like this and hope very hard that they're actually convex. Now, I will give the usual asterisk which says that you don't exactly need convexity, you need a PL inequality, which, for example, for barycenters exists where they're clearly non-convex. So you still have this little bit of a margin of error, but other than that, I think, I don't think there's going to be like I don't really think there's like a very fruitful theory of non-convex optimization. It's just too big, but there will be some classes for which these things work. But I think also, but more importantly, I think we should design functionals for particular problems at hand that actually are convex.
All right, let's cut it off there.
There's a question. Oh, okay.
So it's not a question, but a comment that I want to ask. The Shameless plugin for the Contribution Initiative will offer a PIMS online graduate course on Waterston gradient flows in the fall. It will be taught by me and Young Kim from UBC. So if any of you are interested in this, we'll go over the theory of this thing. So please write to me.
Thank you.